Okay, so for the second part of the lab, we're going to be looking at essentially what happens when we sample repeatedly from a population. And the reason that we're doing this is to get an idea for how each sample varies from sample to sample. So if we have the opportunity to take more than one sample, how much would we expect our two samples to differ by? And we can use this information to get a measure of the amount of uncertainty that we should have when we just have one sample, right? So if we know how all samples tend to be distributed, then we can use that information to get a gauge for sort of how much that difference between samples might be. Therefore, when we have a single sample, we can sort of use that difference as a measure of uncertainty. So the population is students at Massey University. Let's read that in here. And so you can see that we just have three columns. We have their sex, we have their GPA, and we have their age to some ridiculous level of decimal places. And so we're going to start by looking at the proportion of male and females. Okay, so we've got a population here. Our Massey variable was, our Massey data set is 38,675 observations. So we've got 38,675 students. So we're going to start by by having a look at the entire data by doing a bar chart by sex. Okay. So you can see here that in the total data we've got just over 20,000 females and closer to about 18,000 males. So there are a higher proportion of females than males, and then this is computed using this proportion command, which has given us the output 0.5287. So there's about 53% females, right? So more females than males. Okay, so that's in the population, right? Now let's pretend we're in a situation where we don't have the population. We don't have the list of all students at Massey. Instead, what we're going to do is we're going to take a random sample of, say, just 20 students, work out the proportion in our random sample, and then use that to say something about the population. All right, so this next code block is going to take a sample. All right, so samp is a sample. All right, so we just have 20 students, female and male. We've got their GPA and their age and so on. And we're then going to do the exact same thing we've just done, but with the sample instead of the population. And we can then just compare it to what we got before. All right, so here we go. So here in my sample, I had exactly 10 females and exactly 10 males. So the proportion is 50%, right, 0.5. Okay, but of course this is just one sample, and if I took a different one just by rerunning the code block, oh, I got the same proportions. But from time to time I'll get more males. Okay, so this one had 11 males, so the proportion of female is 45%. And in some cases I'll get more females. There we go. Okay, so in this one we had 60% females. Okay, so each time I take a sample of size 20, I'm going to get different individuals in my sample, and therefore a different proportion of male and females, potentially, right? Nonetheless, I'm not getting something wildly off, am I, from my 53%, which is the proportion in the population. Now we're going to automate this process of taking samples, because clicking the button here gets a bit isn't particularly fun. And so we're going to take 20 samples of size 20, and then we're going to plot each of them and work out all of the proportions and so on. Okay, so here we go. So here's our 20 samples of size 20. So you can see that some of the time there's more females, some of the time there's more males, like in 4 and 10, and there's quite a few more males. Okay, and some of the time it's about the same. Okay, and we can get a summary of the proportions across those 20. So you can see that the proportions across those 20 have a mean of 53%, but range from 30% to 70% females. So one of the samples had 70% females, and one or more of the samples had 30% females, so there was quite a range. But if you look at on average across all the samples, we get an average proportion of about 53%. And 53%, you'll remember, is the population proportion. Right, so on average, each of the 20 samples of size 20 that we've taken have been centered or had the similar mean or similar proportion in this case to the actual truth, the population proportion. But there's some spread, there's some scatter around that just due to the sampling process. So we're going to go one step further. Instead of just taking 20 samples of size 20, we're going to take 1,000. So lots of samples. And then we're going to assess what the proportions look like across those 1,000 samples. So what we see is that we've taken 1,000 samples. We've got the proportion. The proportions vary from 0.2 up to 0.95. So in one sample we had 19 females and just one male. And we had as few as 20% female, so that would have been 4 females, 16 male. But again, on average, the proportion is 52.9%, which is very similar to the average in the to the proportion in the population, which is 53%. And you can see that the distribution of the proportions are centered on that true value of 52.8%, and again have that big, large spread. This is the 95, the one that was 95% female. You'll get a slightly different curve to this than I did, of course, because just due to the random variation, right? So it's just because of the randomness, depending on when you run it and what machine you run it on and lots of other things that determine randomness, you'll get a slightly different picture, but it'll look essentially the same. It'll have the same basic shape, right? So we notice that we get this nice sort of bell-shaped curve, bell-shaped histogram. It's centered on the true value of 53% in the population, but it has some spread. And that spread is just representing the basically what happens under random sample-to-sample variation. So this is just what happens by chance when we take samples of size 20. Okay, so we could have a small proportion of females, or we could have a very large proportion of females, but most of the time we have a proportion of females between, say, about 40% and about 65%, right? So let's note that down. So most samples we take look similar to the population with a similar proportion of females. But some are more extreme. We get one here with so the shape of the distribution of proportions that we get is bell-shaped, centered around the true proportion of females, it's 52.8%, but with quite a bit of spread. Okay, so that was samples of size 20. And you would expect, actually, when you only sample 20 people, that you would get those odd cases where you have a very large percentage of females or a very large percentage of males. You'd expect that if we increase that sample size from 20 to something larger, say 100 or something like that, then those sort of freak occurrences where almost everyone is female or male are much, much less likely to happen, right? And they're much more likely to get a proportion that's closer to the truth because you've covered more of the population when you've sampled 100 people compared to 20 people. So we're going to repeat the process, and we're going to take our samples of size 20 again, so 1,000 samples of size 20, then 1,000 samples of size 80, so we're quadrupling the sample size, and then 1,000 samples of size 320, so we're quadrupling the sample size again. And when we do that, we then summarize them. So we compute, we calculate how many proportions there are, proportion of females there are in each of those samples, and then we bind them all up together and do a plot. So let's run that code and have a look and see what happens. Okay, so here's the samples of size 20. We get a distribution that we saw before, right? So it was centered on the true value of 52%, but it had some spread. Okay, notice the spread here isn't quite as extreme as I saw before. That's just chance. Okay, When we increase the sample size, we see a same shape of distribution. So here's sample sizes size 80, and here's sample sizes 320. Same distribution, but now they're much tighter, right? The variability that we have is dropping. So the variability here is quite a bit, and it roughly halves as we go into this one, and roughly halves again as we go into this one. Okay, so the distribution of the sample proportions is centered, is in all cases bell-shaped and centered on the true population portion female of 52.8%. However, the proportion varies between samples due to random sample to sample variation. The amount it varies depends on the sample size. Small samples vary a lot. Big samples vary a small amount. The amount of variation roughly halves for each quadrupling of the sample size. Right, so as we quadruple the sample size from 20 to 80, the amount of variation halves, and as we quadruple it again, it halves again. Okay, so that's proportions, and it turns out that the same thing happens when we look at means as well. Okay, so let's start by looking at the population again, and we'll compute the mean age, which is 28.5, right, 28 years, and the distribution of ages, which you can see is clearly highly skewed to the right. Right, so you've got a few people that are quite old and are at Massey. So, for example, I have a PhD student that's in his 70s. Okay. Right, so that's what the population shape looks like and what the population mean looks like. Now, let's do the same thing. We'll take some samples and see whether we can get back, we can infer from our sample and see whether it lines up with the population. So we're going to skip taking one sample. We're just going to go straight to taking 20 samples of size 20 and having a look and seeing what they look like. So there they are there. So what I notice here is that the shape of these is not all that similar to the shape of the population there. And that's just because the samples are really small, right? These are samples of size 20. And you can see that, you know, if you squint a bit, then you can see that they sort of probably come from that same distribution. But they're just very small samples, and so they're quite noisy, right? And when we look at the sample mean, so if we look at the mean age from group 1 or group 2, sample 3, sample 4, and so on, then we can see that the mean age in these samples varies from about 26 to about 31. We know the truth is, of course, 28.5, and if we average all of the sample means that we've got, so this is sort of the mean of the sample means, we find that the average age is, in fact, very close to the population age. So again, we're seeing the same behavior where each of our samples varies from the truth because we're only taking a sample of the population, not the whole thing. But nonetheless, on the average, the sample means that you get tend to be centered around the truth. Okay, so we can do that when we, so we'll do the exact same thing we did before up here. And we'll run 1,000 samples of size 20, 80, and 320. We'll compute all their means and we'll do a histogram of them. And we can see this same exact shape that we saw before, right? So the samples of size 20, okay, we've taken 1,000 samples of size 20, then obviously we get a lot of different average ages. We get an average age for each of those 1,000 samples, and those average ages vary from under 24 to over 34, right? So vary quite a bit, about 10 units or so. But nonetheless, they're centered around the truth, which is 28.5, the actual population average age. And they follow that nice bell-shaped distribution. Interestingly, they follow that bell-shaped distribution even though the actual samples themselves do not follow a bell-shaped distribution, because of course the samples themselves look something like the population itself. So the population is definitely not bell-shaped, but nonetheless, when we take samples from the population, from that population, and we can compute their sample means, then the distribution of those sample means does follow that nice bell-shaped curve. And we see the similar thing for the size 80 and size 320, and of course the sample-to-sample variation decreases in the same way. Okay, so the distribution of the sample mean is in all cases bell-shaped and centered on the true population mean. The variation in the sample means is highest for small samples, which makes sense, and lowest for large samples, as we're covering more of the population, so sample to sample variation will be smaller. Right, so that all makes sense. And we see that same actual relationship, that quadrupling the sample size seems to halve the sample to sample variation. So what's our conclusion from all of this? What can we say about how you'd expect sample means or sample proportions to be distributed with repeated sampling from a population? Well, what we could say is that we'd expect the sample proportions or the sample means, and it turns out a bunch of other things that we haven't looked at here but are sort of similar in nature. They all follow that nice bell-shaped curve centered on the truth, and the amount of variation depends only on the samples, primarily on the sample size. So how might this help us when we just have one sample, right? Normally we don't have 1,000 samples, because if you think about it, taking 1,000 samples of size 20 is equivalent to taking one big sample of size 20,000, at which point we might as well measure everyone, right? So normally we only have one. Maybe it's bigger than 20, but we only have one sample. Nonetheless, if we have one sample, then we can compute its sample mean, right? So say we only took a sample of size 20, and we wanted to work out what the population mean age was at Massey. Then what we could do is we could work out the sample mean age in our sample of size 20, and it might be as low as 24, or it might be as high as 34, right? It just depends on which sample we happen to have picked. So we don't know whether, it might also be 28, so it might be bang on the money, right? But nonetheless, that's going to be our best guess at what the population mean age is. But because we don't know whether we're actually in the right ballpark or whether we're too low or too high, what we're going to do is we're going to add some uncertainty. And the amount of uncertainty that we're going to add is basically going to depend on the sample size, right? So as we go to a larger sample size, we can get away with adding less uncertainty, because if we add less uncertainty, we're still capturing the sample-to-sample variation. Right, so the idea basically is that we can use this information to derive a measure of uncertainty for a particular sample, or similar, a measure of precision. E.g., if we happened to take a sample of size 20 and wanted to estimate the population average age, we could use the sample average age as a proxy for this, but we don't know if we have a sample where the sample mean is close, e.g. about 28, or if we have one where it is too low or too high. But we know that most sample averages are between, say, 24 and 34, so maybe if we go plus or minus 6 or 5, we might capture the true value even if we started with a sample mean too high. So say it was 33 minus 5, 33 plus or minus 5 is going to be 28 to 38, which captures the truth, just over 28, or too low. So say we had 24 instead, 24 plus or minus 5 is 19 to 29, which again captures the truth, right? Which is just over 28. And of course, if we're in the middle, then we're going to capture the truth using the same criteria. So we use information about the distribution of the sample mean or proportion to derive a measure of uncertainty in the sample mean proportion for the sample that we have. This gives us an estimate of where the population mean or proportion is likely to lie. An interval estimate. So you might have seen these before. They're called confidence intervals, basically. So we'll formalise this up in the lecture on Monday, in terms of what a confidence interval is, and we'll add a little bit of rigor around this this sort of idea that we've explored here. Essentially, just describing exactly the behaviour that we're seeing, and sort of I'll give you what the theory tells us is going to be. We're going to get, which is basically exactly what we see here. So let me just note that. Obviously, I'm going to get a slightly different answer when I do, because different random number generation, but it'll be close enough to the same. There it is there. Okay.